Okay, resonance, and this one is a resonance circuit. And the reason why we might be able to tell this is a series resonant. There are such things as parallel resonance, but in this class, we just do series ones. But it has an R, L, and a C. So this is L, this is C, and it has all three of them. And the resonance frequency is where the reactance of L and C cancel out so that we can maximize our current. And that special frequency, so if I was to plot the current along as a function of frequency, so if I change the frequency, just like you change the frequency of your radio station, and I wanted to achieve a resonant frequency where the current would be maximized, right, and it looks like this. Well, this point right here is FR, or it's also called FS. FS being, say, you can say the special frequency, or R being resonant frequency, and that is where the current is maximized. So the first step is to determine that resonant frequency. On the equation sheet, I think it calls it Fs, but it still uses this equation, 1 over 2 pi the square root of LC. And these problems are easier in some ways in that a lot of the formulas are, or pretty much all the formulas you need are right there on the equation sheet. So when it says I need to know the resonant frequency, I just plug these in. L, 320 microhenries. C, 800 nanofarads. And that resonant frequency comes out to 10 kilohertz, right? So if it's greater than 10 kilohertz, it's not at the resonant. If it's less, along this right here, 10 kilohertz, then it's not at that. So the next one is that we need to solve for Q. Well, Q is equal to X over R. And I said the resonant frequency is where X, I'll write FR when XL equals XC. So that means if I'm at the resonant frequency, then I can use either XL or XC. I'll use XC, 1 over omega C, which is 1 over 2 pi FC, and that would equal 1 over 2 pi. The F that we're using is at the resonant frequency, so 10 kilohertz, 800 nanofarads. That comes out to 20 ohms. So that's XC. If you don't believe me, let's also plug in at that resonant frequency XL, which is omega L, which is also 2 pi FL, 2 pi, the resonant frequency, 10 kilohertz, L, 320 microhenries, and I get 20 ohms. So either way, I just pick one of those two and I can plug it into here. The X, 20 ohms, the R, 1 ohm. So this is Q. It's all, I think on the formula sheet, equation sheet, it says QS because it's the quality of that resonance, and it comes out to 20. So F was 10 kilohertz, Q is 20. Bandwidth on the equation sheet says Fs over QS, 10 kilohertz, QS over 20, and the bandwidth is 500 hertz. The bandwidth being where it's allowed to go through, right? Here's the bandwidth, there's the width right there. In between those right there, if this was the maximum I that could be achieved, then that point right there is where 0.707 I is achieved. So that's what's allowed to go through. There's the bandwidth. Not allowed to go through, but where it's still a high enough quality for us. That's why the bandwidth is based on the quality, a high enough quality that it's still considered within resonance. What's the next part? Says find, we found this, we found this, found this, found the current I at resonance. So I at resonance, well, if XL and XC cancel out, how does that look? right? If we're going to use V equals IZ, doing all the totals. So we're saying I total is that E is the source, is that V total. So what is Z total? Well, Z total is 1 ohm plus J20 minus J20. So all that's left is 1 ohm, right? And that makes sense. If you wanted to just write the R, that would also be acceptable, because the final Z total at resonance is when the X's equal each other and they effectively cancel out. So 10 volts, angle 0 over 1 ohm, and I get 10 amps. And technically that'd be 10 amps, angle 0. Okay, so there's the parts. The last one is plot the current versus frequency and label the resonance, F1, F2, and the bandwidth. I basically labeled those. The only thing I haven't labeled is the width of these. So if this is 500 hertz, there is an equation for it where it says the FR plus or minus the bandwidth divided by 2. You can kind of almost just see that. If this is 9.75 kilohertz on one side and 10.25 kilohertz on the other side. Right, so the resonant frequency plus or minus the bandwidth divided by 2. Well, that makes sense. If I'm at 10 in the middle, I go 250 either way, and there's my whole current that's been plotted. So this is I max, this is 0.707 I max.